Hello. So today what we're going to be talking about is something called numerical integration. So sometimes we're still given functions even though we just learned about the use substitution method for integration that we don't know how to integrate. So if we want to find what the area under the curve is, we need to use an approximation method. So before we were using the Riemann sum to approximate area, which was we broke the interval up into different amounts of rectangles and then added up the area of all of the rectangles. So today we're going to learn two different methods to approximate the area under a curve, and they're called Trapezoidal Rule and Simpson's Rule. So we're going to start out by first looking at an example of a function for two things. So if we have a function like this, do my best to copy it right over here, and say we were looking at the points from A to B. So it looks just about the same over here. So the first thing we're going to do is we're going to split it up using rectangles. So say I split this up into 4 pieces, and I use my left hand endpoints. So if I draw the rectangles in, I get something like this. So the rectangles look like they're covering a lot of the area, but if I shade in the area that's not being covered so far with green, we have a lot of area here that's actually not being covered. But now what happens if I split the same interval up into 4 intervals and instead draw trapezoids? So if I draw the lines up and draw trapezoids connecting them, we can see that we actually have a lot less area being missed. Even with only 4 trapezoids, we only have a little bit of area here, maybe a line there and a line there, maybe a little bit here that's not being covered. So there's a lot less green area. So the reason now that we're going to use something called the trapezoidal rule is because if we approximate it with trapezoids, we're going to get a lot closer. So now we're going to go over what the definition for the trapezoidal rule is. So the definition of the trapezoid is we're going to sum up the area of different amounts of trapezoids. So if we let Ti be just one trapezoid, the area of that is going to be, the area of a trapezoid is just always 1/2 times the sum of the bases, which in this case are 2 heights. So f of xi plus f of xi plus 1. And then times the base, or the width of the trapezoid, which in this case is just going to be xi plus 1 minus xi. But if we simplify that, that's really just 1/2. And then this quantity over here is just delta x, because it's the difference between 2 consecutive x's that we're partitioning our interval up into. So we're going to get 1/2 delta x times f of xi plus f of xi plus 1. Now if we add up an I amount of these, or if we add up n amount of trapezoids, our formula for the trapezoidal rule is going to say that the integral from a to b of f of x dx is just going to be approximately equal to 1/2 delta x times f of x naught plus 2 f of x1 plus 2 f of x2 plus dot 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 all the way up to 2 f of x n minus 1 plus f of xn. So you maybe say, why are there 2's in front of all of them but the first and the last one? And if we look back at our picture here with our trapezoids, we can see that all of these green lines are in two trapezoids. So they'd be counted twice, whereas these red ones on the end are only in one trapezoid, so they're only counted once. So like over here, this is x0, x1, x2, x3, and x4. So x0 and x4 are only in one trapezoid each, whereas x1, x2, and x3 are all in two, so they have to be counted twice. So now we're going to see how this works with an example problem. So we're going to use the trapezoidal rule and n equaling 4 to approximate the area under the curve from 1 to 3 of the square root of x, which is graphed over here at the left. So we want to approximate the area under here. So the first thing we want to do is find our delta x. So delta x, as always, is just going to be equal to b minus a over n. It's what it always is equal to for us. So that's just going to give us 3 minus 1 over 4, which is 2/4 or 1/2. So if I start at 1 and I go over 1/2 each time, I'm going to get 1 is going to be 1, 1.5, 2, 2.5, 3. So now if I draw in my trapezoids by first drawing up the lines from each of these xi's and then connecting them, we can see that it's a really close approximation. Now, I didn't mention this on the last page, but your formula for xi is always just a plus delta x times I. So in this case for us, it's going to just be 1 plus 1/2 I. And you start plugging in for I from 0 and go all the way up to n. So to use the trapezoidal rule, this is just going to come out to be, the integral is going to be approximately 1/2 times delta x, which for us we know is 1/2, times f of x0. x0 is just 1 plus 0, so 1, plus 2, times, if we plug in 1 for I, we're going to get 1 plus 1/2, or 3/2, plus 2f. If we plug in 2 for I, we're going to get 1 plus 1, which is 2, plus 2 times f of going over another 1/2 is going to give us 5/2, plus finally f of going over one more half is going to give us f of 3. So now if we simplify this, this is just approximately 1/4. And if you use your graphing calculators to figure out the function values at 1, 3/2, 2, 5/2, and 3, and multiply them by the proper coefficients, we're going to get that this is just 1/4 times 11.172, taking out to 3 decimal places, which is approximately 2.793. This is a really easy function to do, and it's really nice because we could actually use the first fundamental theorem of calculus to get an accurate answer for what the area from 1 to 3 is under the square root of x. But this is just a good way to approximate it. And doing these easier functions is a great way to see how it works because you could check your answer really easily by actually doing the integration. So now we're going to talk about the second numerical integration method that you guys might be learning about, which is Simpson's method. So I'm not going to go through how Simpson's method is developed, but something that's important to know is that if you look at the trapezoidal rule, when we draw in the trapezoids, the lines that are really close to the curve are straight lines, or linear or first degree polynomials. So Simpson's method is based off of the fact that we can approximate these curves using quadratic functions during each interval. So we're going to use a second degree polynomial instead. And the formula you really need to know, though, is that the integral from a to b of f of x dx for Simpson's rule is just approximately 1/3 of delta x times f of x0 plus 4 f of x1 plus 2 f of x2 plus 4 f of x3. So we're getting this repetition between the 4 and the 2 plus 2 f of x to the n minus 2 plus 4 f of x n minus 1, finally plus f of xn. So some important things to note here is that delta x, again, is going to be always, whoops, forgot the x, b minus a over 2. To find our xi, we're again just going to do a plus delta x times I. And then what's really important for Simpson's rule is that n has to be even. So this is really important. So you can only do n for like 2, 4, 6, 8, 10, 12, and so on for Simpson's rule. And Simpson's rule we're going to see about the next topic that we talk about, which is going to be analyzing the error of both trap rule and Simpson's rule. We're going to see that the trapezoidal rule tends to be a lot more accurate than trapezoidal rule. And so what's important to realize is that for the pattern for Simpson's rule is your first x naught and your last one, you only put them in once. But then in between, you repeat between 4, 2, 4, and then your last coefficient before your last xn should always be a 4, which is why n has to be even. If it's odd, the pattern doesn't work out quite as well. So this might seem really confusing, especially because I didn't go over how Simpson's rule is developed, but hopefully your professors are doing that. So if you have any questions about that, I would go ask your teacher because it is a longer explanation. And so now what we're going to do is an example, the same example as before using Simpson's rule now to see how this works. So we know from the same example that we just did that we're just doing the area under here. We know that delta x is just 3 minus 1 over 4, which is 2/4 or 1/2, which means that if we split this up by going over, we're going to get x0 is 1, x1 is 1.5 or 3/2, x2 is going to be 2, x3 is going to be 5/2, and then x4 is going to be 3. So now we can substitute in with Simpson's rule and get that this is just going to be 1/3 times delta x, which is 1/2, times f of x naught plus 4 f of x1 plus 2 f of x2 plus 4 f of x3 plus 1 f of x4 for our final one. So if we plug in, this is approximately going to be equal to 1/6 times the square root of 1 plus 4 times the square root of 3/2 plus 2 times the square root of 2 plus 4 times the square root of 5/2 plus the square root of 3. And I got all of those numbers just simply by plugging in what all of our xi's were. So x0 is 1, x1 is 3/2, x2 is 2, x3 is 5/2, and x4 is just 3. And I got that again by using that formula where xi is equal to a plus delta xi, or 1 plus 1/2 I in this case. And you start plugging in with I equaling 0 and continue on until you get to n. So again, if you use your graphing calculator to figure out what all these function values are and you add them together, you get that this is 1/6 times 16.784, which is just going to be equal to 2.797. Which, if you remember from when we did the trapezoidal rule with this problem, we got 2.793. So you might be asking yourself, well, how accurate is this? So which one is closer? Which the next thing we're going to go over is the error analysis. But if you go to your graphing calculator and you use that to integrate the square root function from 1 to 3, let's see what we're going to get for our answer. Our answer then is 2.7974. So this is really close. I think the accuracy for Simpson's rule for this problem is out to the 4th or 5th decimal place. So now we're going to use different formulas to figure out how accurate these are, so what the error is. So we're going to do error analysis for both the trapezoidal rule and the Simpson's rule. So to do the error analysis for trap rule, that's the top one here, your function has to have a continuous second derivative on the interval. And then to evaluate the error, which we call E, in approximating the area, that formula is simply going to be that the absolute value of E, so E is always going to be a positive number now, is simply just going to be less than or equal to B minus A over 12 times delta x squared times the absolute value of the maximum value of the second derivative over the interval. And if that seems really confusing, don't worry, we're going to do an example problem in a second to show you how it works. And then to evaluate the error for Simpson's rule, the function has to have a continuous fourth derivative. So this should really be written as f with this like here. So if the function is a continuous fourth derivative on the interval, then the error E in approximating the definite integral from a to b is given by the absolute value of E is less than or equal to b minus a over 180 times delta x to the fourth, again times the absolute value of the maximum of the fourth derivative over the interval. So delta x is usually a pretty small number. So we can see from these error analysis rules why the Simpson's rule tends to be more accurate, because for delta x really small, delta x raised to the fourth down here is going to be a much smaller number than delta x squared. So our error is always going to be much smaller. So now let's do an example and see how this works. So we're going to do the error analysis for both the trapezoidal rule and Simpson's rule for the problems that we've already done. So n equaling 4 for the definite integral of 1 to 3 of the square root of x. So let's do the trap rule formula first. So using the formulas that we just talked about, we know that E is less than or equal to B minus A over 12 times delta x squared times the max, the absolute value of the maximum of the second derivative of x. So what we need to do now is we need to find our first and second derivative. So our first derivative of the square root of x is just 1/2 x to the negative 1/2. So our second derivative using the power rule is going to be equal to negative 1/4 x to the negative 3/2. So this is always, on the interval from 1 to 3, the second derivative is always negative. So we're not going to have any critical values. So that means that the maximum of it is going to be at an endpoint, since we don't have any critical values on the interval. So if we plug in for 1 and 3, the second derivative of 1 is negative 1/4, and the second derivative of 3 is equal to negative 1 over 12 times the square root of 3. And negative 1/4 is a bigger number than negative 1 over 12 square root of 3. So that's the value that we're going to use for the maximum in here. So now all we have to do is plug in. So we can say that the absolute value of our error is going to be less than or equal to B was 3 and A was 1. So 3 minus 1 over 12. Delta x was 1/2 squared. And then we're going to square it. And then we're going to multiply by the absolute value of negative 1/4, because we determined that that was the maximum value of the second derivative on the interval from 1 to 3, which is going to give us that the absolute value of E is just equal to 2 over 12 times 1/4 times 1/4, which we can cancel this 2 and 12 and make this a 1/6. So we're going to get that E is less than or equal to 1/6 times 1/16, which is simply going to be 1 over 96. So that's pretty accurate, that the error for the trapezoidal rule is within 1/96th of the actual error, the actual area rather, of that definite integral. So now let's do it with Simpson's rule and see just how more accurate Simpson's rule is. So for Simpson's rule, we have that the formula is that absolute value of the error is less than or equal to B minus A over 180 times delta x to the fourth times the absolute value of the max of the fourth derivative. So I ran out of room. Whoops. So first we need to know what the third and fourth derivative is then. So f triple prime of x, if we keep working off what we found for the second derivative above for the trapezoidal rule, we can easily find that the third derivative is just going to be positive 3/8 times x to the negative 5/2, which means that our fourth derivative of x is just going to be equal to negative 15 over 16 x to the negative 7/2. So again, there are no critical values. The fourth derivative is never going to be undefined or equal to 0 on the interval from 1 to 3. So that means by the extreme value theorem that the maximum has to happen at an endpoint. So if we look at the fourth derivative value of 1, we're going to get that it's just negative 15 over 16. And if we look at the fourth derivative value of 3, once we simplify, we're going to find that it's equal to negative 5 over 144 times the square root of 3. So again, our maximum value is going to be at 1, so we're going to use the absolute value of negative 15 over 16 in our error formula. So that means our error formula now is going to be that the absolute value of the error is less than or equal to b minus a, so it's less than or equal to 3 minus 1 over 180 times delta x, which was a half raised to the fourth, times the absolute value of the maximum of the fourth derivative, which we found was negative 15 over 16. Now all we have to do is simplify. So I'm going to get that the absolute value of the error is less than or equal to 2 over 180 times 1/16 times the absolute value of negative 15 over 16 is just positive 15 over 16. So now if we go about simplifying, we can cancel the 2 with the 180 and get 1 over 90. And then we can cancel between the 90 and the 15 eventually. So when we finally simplify our error, we're going to get that the error is less than or equal to 1 over 1536. So 1 over 1536 is a much smaller number than 1 over 96. So we can see that even for a small number of trapezoids or partitions, like n equaling 4, the Simpson's rule is much more accurate than the trapezoidal rule. And as you let n get bigger, these error values are going to get even smaller. So you're going to get really close to the accurate definite integral values. So I hope this helped explain how to do trapezoidal rule and Simpson's rule and then how to analyze the error for both of them. But thank you so much for watching. Have a great rest of your day.